Hello, and welcome back to the second part of this course, Classical Electromagnetism. So we are still on the fourth chapter for this course. Before we proceed with today's lesson, let us first review some of the concepts that we have discussed earlier. So we have discussed about the force on moving charges. So when a moving charge with velocity v is exposed to a uniform magnetic field B, then the external magnetic field will exert a force on that moving charge. So if the velocity is zero, if the charge is not moving, then there's no magnetic force. If the velocity is parallel to the external magnetic field vector, then there will also be zero magnetic force. So for today's lesson, we will be focusing on this concept, the magnetic force on moving charges. But we will delve deeper into more advanced application and examples. Okay, so if the velocity of the moving charge is perpendicular to the magnetic field, then what you get is a uniform circular motion. So if this is the original position of your moving charge, it's moving to the right. So, and the magnetic field is in this direction, it's actually into the plane. So you make a cross product, V cross B, and you get F is upward. So since the charge is moving to the right, but there's a magnetic force pushing it upward, then it will curve in this direction. So you will notice that at every point, the force is actually directed always towards a common center, hence forming a circular motion. So this force here is usually what we refer to as centripetal force. So it's undergoing a centripetal acceleration. Now, if the velocity has both perpendicular and parallel components to the magnetic field, then the motion is a helical motion. Take note that the parallel component is unaffected by the magnetic field. So meaning the parallel component of the velocity will still remain. So it will undergo a circular motion plus a motion, the parallel motion. So hence that motion is what we refer to as helical motion. So this is the helical motion if it's a positive charge. If it is a negative charge, then it will undergo helical motion but in the opposite direction. So this has a very significant application with respect to the Earth's magnetic field. So if the Earth is bombarded by charged particles, then those positive and negative charged particles will just undergo helical motion towards the poles, the magnetic poles of the Earth. And when these charged particles undergoing helical motion towards the poles interact with the atmosphere of the poles, they produce a very beautiful phenomenon called aurora. Aurora borealis for northern lights, aurora australis for southern lights. Now, the magnetic force actually do no work. So what does this mean? So take note, work is defined as the integral of F dot the displacement dl. So if you take F dot dl of this magnetic force, you will get 0. So this means that the magnetic force cannot alter or cannot change the magnitude of the velocity of the charge. So it will still have the same magnitude, uniform magnitude, but the direction will change. So the only thing that the magnetic force can alter or can change is only the direction of the velocity, but it cannot alter or change the magnitude of the velocity. So that's what it means by the magnetic force doing no work. So if the charge is now moving, so work on the charge or by the charge is actually not due to the magnetic field, as opposed to the electric field. An electric field does work. It does work on a charge, but the magnetic field doesn't do any work. So it means other forces are doing work aside from the magnetic force. So let's have an example. So the circular motion that we have presented earlier is also called a cyclotron motion. So in this example, we are asked to find the angular velocity, or sometimes referred to as the cyclotron frequency, of a charge Q moving in circular motion in a uniform magnetic field B, assuming that the velocity is perpendicular to the magnetic field. So how do we do this? Okay. So we know that the magnetic force on this charge is Q, the charge, and then V cross B. And since in this case, the velocity vector is perpendicular to the magnetic field vector, then the magnitude will just be QVB. This is the magnitude of the force. Now, I have mentioned earlier that this force is a centripetal force. So a centripetal force is just M V squared over R. So this is the centripetal force in uniform circular motion. So if we divide both sides by V and multiply by R, we can actually get the momentum, mv, and it's equal to qbr. So this is the cyclotron momentum, the momentum of the cyclotron. Now, in uniform circular motion, the velocity is actually related to the angular velocity by the radius. So this is the relationship between the linear velocity and the angular velocity. This is actually what we are trying to find, the angular velocity. So if you replace v here with r omega and solve for omega, then we can get omega is equal to qb over m. So this is actually the cyclotron frequency. So this is actually what is asked in the problem, the cyclotron frequency. And you will notice that it only depends on the magnitude of the charge, the magnetic field, and the mass of that charge, and nothing else. It only depends on these three constants. So as a summary, this is the cyclotron momentum, this is the cyclotron frequency. Now moving on to another example. So this example is about Thomson's EM apparatus. E is the charge, M is the mass. So basically it's a charge to mass ratio apparatus, EM apparatus. So in this apparatus, a beam of electrons from a source goes through an electromagnetic field. So here, the electric field is from the upper plate to the lower plate. So the electric field is downwards, and the magnetic field is into the pitch. So the electric and magnetic fields are perpendicular to each other. So if the electric and magnetic fields are adjusted, just that the charge will not be deflected. So the charge will just remain straight. It will not be deflected. It will not, meaning it will not experience any force. Then what is the speed of the electrons? Okay, so in this scenario, the total force will actually be due to the electric force plus the magnetic force. And in this case, the total force, or the Lorentz force, is 0. So here, our Q is, since this is electron, so it's negative E. So that's our charge, negative E. So this means that say negative E times E equal to E times V cross B. So we transpose this part to the other side of the equation. Or sorry, this one we transpose to the other side of the equation. It becomes from negative Q is negative E. So negative E transpose, it becomes positive E. Divide both sides by E, and we get this one. E is equal to negative V cross B. Now, since in this case, the velocity is perpendicular to the magnetic field, then the magnitude of V cross B is just V times B. And the magnitude of the electric field is just E. So this is just essentially E equal to V times B. And then we can now solve for the velocity of the electron. It's just E cross B. So when the electric fields and magnetic fields are adjusted such that the electrons are not deflected, experiences zero force, then the speed of the electrons is given by the magnitude of the electric field over the magnitude of the magnetic field. So that is the speed of the electron. So usually we call this application as the velocity selector. So it actually determines the speed of the electrons depending on the magnitude of the electric and magnetic fields. So you can actually adjust the speed of the electrons by just adjusting the electric and the magnetic field magnitudes. Okay, how about for the second question? If the electric field is turned off, the beam will now undergo circular motion with radius r due to the magnetic field. So it will undergo cyclotron motion because there's no more electric field, only magnetic field. So what is the charge to mass ratio of the particles? So this is assuming that you measure the cyclotron radius, assuming that you know r. So assuming that you measured the cyclotron radius r, and you are asked to find the charge to mass ratio. So the magnitude now of the force will just be QVB, since the velocity is perpendicular to the magnetic field. So it's just EVB. So it's just magnitude, no longer not needed to include the negative sign. And this is equal to the centripetal force, mv squared over r. Okay, so if we only measure E over m, so divide by m and VB, so divide by m and VB, and we will get V over B r. So this is the cyclotron frequency, charge to mass ratio in terms of the velocity. But since we already know the magnitude of the velocity of the electron, take note, the magnitude doesn't change, only the direction, because the magnetic force does no work. So the magnitude is E over B. So this is E over B. So essentially, the charge to mass ratio of an electron is equal to E over B squared r. So this is now the charge to mass ratio of an electron with respect to this apparatus. So you can measure the charge over mass ratio of the electrons by just knowing the electric field before you turn it off, the magnitude of the electric field, the magnitude of the magnetic field, and the radius of the cyclotron motion after you turn the electric field off. So that's the charge to mass. That's how Thomson measured the charge to mass ratio of an electron. So as a summary, this is the speed of the electrons, and this is the charge to mass ratio of the electrons for this given apparatus. So for our last example, so we have a particle of charge Q, and initially it's moving to the right with velocity v, and then it enters a region with uniform magnetic field. So this is the field region. The width of the field region is A. And when the charge enters the field region, it becomes deflected. And actually, after it exits the region, the field region, it's now a distance d above its original axis. Okay. So the question now is the charge positive or negative? So what do you think? So V cross B. So when the charge enters here, you perform a V cross B. So using right-hand rule, V cross B, magnetic field is into the page. So you get up. So if it's positive, it's deflected upward, then it's positive. If it's deflected downward, then it's negative. So in this case, since it's deflected upward, then it's a positive charge. Now, find the momentum of the particle in terms of the width of the field region A, this distance d, and the magnitude of the magnetic field B, and the charge of the particle Q. So we are now trying to find the momentum. Okay. So take note that this curvature here is actually a circular curvature, and it has a center here, say here. So the distance to here, this is R, and the distance to here, that's also R, since that is a part of a circle. Okay. So we need to actually solve for R first in terms of A and D. So how do we do this? So if this is A, that is A, and this is, if this distance is D, then this distance is R minus D. So this is R minus D. So we have a right triangle here. And from this right triangle, we can actually solve for R. So from here, we have R squared, the hypotenuse, this side is actually equal to the square of this side, which is R minus D, plus A squared. So solving for R, you will get, I will leave this to you, A squared plus D squared over 2D. So you can now write the radius R in terms of A squared plus A and D. Now, going back to the starting point, so this force is just QVB. The magnitude of the force is just QVB. And this is equal to the centripetal force, mv squared over R. So meaning the momentum P, which is mass times velocity, is just QBR. And since we already know what is R in terms of A and D, then P is just equal to QB times R, which is A squared plus D squared over 2D. So this is now the momentum of this particle as it exits the field region. So QB A squared plus D squared over 2D. So after it exits this region, it will now move in a straight line. It will not be deflected because there's no longer any magnetic field here. So after it exits the field region, it will just move in a straight line. So with the same velocity still, V, but the momentum is now given by this value. It's actually a constant. It will have a constant momentum and a constant velocity. Okay. So in summary, this is the momentum of the particle as it exits the field region. So that is it for this lesson. So for the next lesson, we'll now be dealing with current carrying conductors. So I will see you again in the next lesson.